April 10th, 2019, a hush fell over simultaneous press conferences in 6 cities across the world: in Brussels, Tokyo, Shanghai, Taipei, Washington, and Santiago. Scientists prepared to reveal something that had never been seen before. Then the image appeared on screens everywhere: a glowing orange ring, slightly brighter on one side, surrounding a perfect darkness. The first photograph of a black hole. Newspapers ran it on their front pages. The image broke download records on the National Science Foundation's website. People who had never thought twice about astrophysics suddenly understood something profound about our universe. We had seen the unseeable. Except we hadn't. What the Event Horizon Telescope captured that day was not a photograph of a black hole. It could never be a photograph of a black hole, because photographing a black hole directly is not just difficult, not just beyond our current technology. It is fundamentally, absolutely, physically impossible. The very definition of what a black hole is makes it so. This is the story of why we will never see a black hole, and how we photographed one anyway. To understand why you cannot photograph a black hole, you first have to understand what photography actually is. Every photograph ever taken is a record of light. When you snap a picture of your coffee cup, what you're actually capturing is the light that bounced off that cup and traveled into your camera's sensor. The cup itself stays where it is. What reaches your camera is information carried by photons. This seems obvious until you think about what it implies. You cannot photograph anything that doesn't emit or reflect light. In a perfectly dark room with no light sources, no camera in existence can capture an image of what's inside. Not because the technology isn't good enough, but because there's literally nothing for it to capture. Now consider a black hole. A black hole is a region of space where gravity has become so overwhelmingly strong that the escape velocity, the speed you'd need to travel to break free, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. Not matter, not radiation, not information of any kind, including photons. This is what we mean by the event horizon, the boundary around a black hole beyond which light cannot escape. The name is poetic but precise. It is the horizon beyond which no events can ever be observed. Cross that line, and you are gone from the universe forever, as far as the rest of us are concerned. The term event horizon was coined by physicist Wolfgang Rindler in the 1950s, and it captures something essential about the nature of black holes. It's not just that light can't escape, it's that causality itself becomes one-directional. Inside the event horizon, all paths forward in time lead deeper into the black hole. Moving away from the singularity becomes as impossible as moving backward in time. This is difficult to visualize because our everyday intuitions don't prepare us for it. We think of space as something we can move through in any direction. But inside a black hole, the direction toward the center becomes as inescapable as the direction forward in time. Trying to move outward would be like trying to travel into your own past. So when we talk about photographing a black hole, we face an immediate problem. Photography requires light. Black holes emit no light. They reflect no light. Light that enters them is captured and never returns. Think about what this means. If you shined a flashlight at a black hole, the light would simply vanish. If you took a photograph with a flash, The flash would disappear into the void. The black hole would reveal nothing of itself. It wouldn't scatter your light. It wouldn't absorb and re-emit it. It would simply swallow it, adding the photon's energy to its mass, growing ever so slightly larger. You cannot photograph darkness itself. You can only photograph the absence of light against a background of light. This is exactly what the Event Horizon Telescope did. The idea that an object could be so massive that light couldn't escape from it is surprisingly old. In 1784, an English clergyman and geologist named John Michell wrote a paper for the Royal Society proposing what he called dark stars. Using Newton's laws of gravity and treating light as particles with mass, Michell calculated that a star with the same density as the Sun, but 500 times larger, would have an escape velocity exceeding the speed of light. Such an object, he wrote, would be invisible to distant observers. It was a remarkable insight, but it was also wrong. Newton's physics couldn't properly describe what happens when gravity becomes extreme. That would require a new theory of gravity, one that wouldn't arrive for another 131 years. In November 1915, Albert Einstein published his general theory of relativity. It was a complete reimagining of what gravity actually is. Newton had described gravity as a force pulling objects toward each other across empty space. Einstein proposed something stranger, that massive objects warp the fabric of space and time itself. And what we experience as gravity is simply objects following the curved paths through this warped space-time. Within weeks of Einstein publishing his equations, something remarkable happened. Karl Schwarzschild was a German physicist and astronomer, one of the leading scientists of his era. But in 1915, he wasn't in a laboratory or observatory. He was serving in the German army on the Russian front during World War I, calculating artillery trajectories between fierce battles. Despite his circumstances, Schwarzschild obtained Einstein's new paper and began working through the mathematics. Einstein himself had only found approximate solutions to his own equations. Believing exact solutions would be extraordinarily difficult. But in a letter dated December 22nd, 1915, Schwarzschild wrote to Einstein that he had found an exact solution. As you see, Schwarzschild wrote, the war is kindly disposed toward me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, to take this walk into this, your land of ideas. Einstein was astonished. I had not expected, he replied, that one could formulate the exact solution of the problem in such a simple way. Schwarzschild's solution described the geometry of space and time around a perfectly spherical, non-rotating mass. And buried within his mathematics was something peculiar, a special radius where the equations behaved strangely. At this distance from the center of the mass, something curious happened to the metric describing space-time. This radius would come to be called the Schwarzschild radius. It marked the boundary we now know as the event horizon. The Schwarzschild radius has a surprisingly simple formula. It equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For our Sun, the Schwarzschild radius works out to about 3 kilometers, meaning that if you compressed all the Sun's mass into a sphere 3 kilometers across, its surface would become an event horizon. Earth's Schwarzschild radius is even more striking, about 9 millimeters. If you could somehow compress our entire planet to the size of a marble, it would become a black hole. These calculations seemed absurd to early 20th century physicists. What force could possibly compress matter so thoroughly? The mathematics might allow such objects, but surely nature would never create them. Schwarzschild himself didn't fully grasp what his solution implied. Neither did Einstein. Most physicists of the era assumed the strange mathematical behavior at this radius was just a quirk of the equations, not something that could actually exist in nature. Einstein himself would later write a paper attempting to prove that black holes were impossible, an ironic footnote to the theory whose equations first predicted them. Schwarzschild never had the chance to explore the implications of his work. He had contracted pemphigus, a painful autoimmune disease, while serving in Russia. He was invalided home in March 1916 and died 2 months later at the age of 42. His solution lived on, waiting for future generations to understand what he had found. For decades, physicists argued about what the Schwarzschild radius actually meant. Was it real? Could an object actually collapse to such a state? In 1939, Robert Oppenheimer and his student Hartland Snyder published a landmark paper showing that when a sufficiently massive star exhausts its nuclear fuel, nothing can stop its gravitational collapse. The star will shrink past its Schwarzschild radius, forming what they called a frozen star. From the perspective of a distant observer, the collapsing star would appear to slow down, its light becoming increasingly redshifted until it seemed frozen at the edge of oblivion. But even Oppenheimer and Snyder didn't fully appreciate what they had described. The physics community remained skeptical. Arthur Eddington, one of the most prominent astrophysicists of the era, insisted there should be a law of nature to prevent a star from behaving in this absurd way. It wasn't until 1958 that physicist David Finkelstein clarified what was really happening. The apparent freezing of the collapsing star was an illusion created by the warping of time. From the perspective of something falling in, time continued normally. The event horizon, Finkelstein wrote, is a perfect unidirectional membrane. Causal influences can cross it in only one direction. One way in, no way out. The objects still needed a name. Physicists had been calling them gravitationally completely collapsed objects, a mouthful that captured none of their strangeness. Various alternatives circulated: frozen stars, dark stars, collapsed stars. Then, in December 1967, physicist John Wheeler was giving a lecture at NASA's Goddard Institute of Space Studies in New York. He kept repeating the phrase gravitationally completely collapsed object, growing increasingly frustrated with its awkwardness. "How about black hole?" someone in the audience called out. Wheeler immediately recognized the perfection of the term. "I had been searching for just the right phrase for months," he later wrote, mulling it over in bed, in the bathtub, in my car, wherever I had quiet moments. Suddenly, this name seemed exactly right. He used the term in a lecture at the American Association for the Advancement of Science a few weeks later, and included it in the written version published in 1968. The name caught on instantly. Black holes had been christened. Now someone had to find them. The challenge of detecting a black hole might seem straightforward. They're black. Space is black. How do you find a dark object against a dark background? The answer lies in what happens around a black hole, rather than inside it. While black holes themselves emit nothing, they dramatically affect their surroundings. When matter falls toward a black hole, it doesn't simply plunge straight in. Conservation of angular momentum causes it to spiral inward, forming a swirling disk of material called an accretion disk. This disk becomes extraordinarily hot. As matter spirals closer to the black hole, it accelerates to tremendous velocities, particles colliding with increasing frequency and violence. The friction and compression heat the innermost regions of the disk to temperatures of millions of degrees. For stellar mass black holes, temperatures can reach 100 million Kelvin, more than 6 times hotter than the core of our Sun. For some configurations, temperatures can exceed billions of degrees. The physics here is remarkable. Matter in an accretion disk moves at a significant fraction of the speed of light. The innermost stable orbit around a non-rotating black hole sits at 3 times the Schwarzschild radius. Any closer, and the orbit becomes unstable, with matter plunging rapidly toward the event horizon. For a spinning black hole, that innermost stable orbit can be even closer, allowing matter to accelerate to even more extreme velocities. The energy released is staggering. Accretion onto a black hole can convert about 10 to 40% of a particle's rest mass into radiation, far more efficient than nuclear fusion, which converts less than 1%. This is why active black holes, feeding on surrounding gas, can outshine entire galaxies despite their compact size. At these temperatures, the accretion disk doesn't just glow. It blazes with radiation, primarily in the X-ray spectrum. A black hole that is actively consuming matter can outshine its entire host galaxy. The center of the Milky Way, where Sagittarius A star lurks, would be visible from other galaxies if our black hole were actively feeding. Currently, it's relatively quiet, a slumbering giant with only wisps of gas to consume. This is how astronomers first found evidence for black holes. In the 1960s and 70s, X-ray telescopes detected intense radiation sources that could only be explained by matter falling into extremely compact objects. The binary system Cygnus X1, discovered in 1964, became the first widely accepted black hole candidate. Something was there, something massive and compact, something that emitted no light of its own, but whose gravity caused nearby matter to scream with X-ray radiation as it fell toward oblivion. But detecting X-rays from an accretion disk is not the same as seeing a black hole. It's like inferring the presence of a drain in a bathtub by watching the water spiral down. You know something is there. You can study its effects, but you cannot see it. What astronomers wanted was an image, not of the X-rays, not of the stars orbiting at safe distances, not of the jets of plasma shot out at relativistic speeds. They wanted to see the shadow, the silhouette, the darkness itself, the idea of actually photographing the region around a black hole had been simmering in the astrophysics community for decades. The theoretical framework was clear. If you could observe a black hole surrounded by luminous material, you should see a dark silhouette, a shadow, where the black hole blocked and bent light. But how dark? How large? What shape? These questions required careful calculation. The mathematics of light in the vicinity of black holes is governed by general relativity. Photons, massless particles of light, follow curved paths through the warped space-time around a black hole. A photon passing close to a black hole will be deflected from its original course. The closer it passes, the more it bends. Get close enough, and the photon will spiral around the black hole multiple times before escaping or plunging in. James Bardeen, a physicist at the University of Washington, worked out the mathematics of what a black hole would look like against a background of stars in 1973. He showed that the apparent size of the dark region would depend on the black hole's mass and spin, and that the shape of the shadow for a spinning black hole would be slightly asymmetric, a result of frame dragging, where the rotating black hole pulls space-time itself around with it. In 1979, French astrophysicist Jean-Pierre Luminet created the first simulated image of what a black hole with an accretion disk might look like. Using a computer at the Paris Observatory, a machine far less powerful than the phone in your pocket, he calculated how light rays would bend in the extreme gravitational field. The computation took hours for each individual light ray, and he plotted thousands of rays to build up a complete picture. The resulting image was haunting. The accretion disk appeared warped and asymmetric, one side brighter than the other due to the Doppler effect, as material on one side of the disk moved toward the observer, while the other side moved away. Light from behind the black hole was bent up and over it, creating the illusion of a halo. The top of the disk, which should have been hidden behind the black hole, appeared to wrap over and become visible. The bottom of the disk was similarly distorted, and in the center, darkness, a void where no light emerged. Luminet drew the image by hand using India ink on negative paper, a stunning artistic achievement as well as a scientific one. The image appeared on the cover of Astronomy magazine in 1979 and captured the public imagination in a way that equations never could. But Luminet's image was theoretical, a calculation of what we might see, rather than an observation of what was actually there. The real question was whether such a shadow could ever be observed. Enter Heino Falcke. In the 1990s, Falcke, then a young German astrophysicist, began studying the supermassive black hole at the center of our galaxy, known as Sagittarius A star. This black hole, containing about 4 million solar masses, lurks 27,000 light-years away, hidden behind dense clouds of gas and dust that block visible light. But radio waves can pierce through that cosmic fog, and Falcke realized something important. At certain radio frequencies, radiation from near the event horizon could escape through the surrounding material. The interstellar medium that blocks visible light becomes progressively more transparent at shorter radio wavelengths. At millimeter wavelengths, the universe opens up. Working with colleagues at the Max Planck Institute and later at various American universities, Falcke developed detailed models of what Sagittarius A star should look like at different wavelengths. His calculations showed that the emission region was shrinking as the wavelength decreased, getting closer and closer to the event horizon. At millimeter wavelengths, the emission should come from right at the edge of the black hole's shadow. In 2000, Falcke published a landmark paper with colleagues Fulvio Melia and Eric Agel in the Astrophysical Journal Letters. The paper was titled "Viewing the Shadow of the Black Hole at the Galactic Center," and it laid out a vision that would take nearly 2 decades to realize. They showed that if a black hole were surrounded by glowing material, whether an accretion disk or a more diffuse emission region, it would cast a shadow. This wasn't the shadow we encounter in everyday life, cast by an opaque object blocking a light source. It was a shadow created by the black hole capturing light, a dark silhouette where photons had fallen in and never returned. The paper made specific predictions. The shadow should be about 5.2 Schwarzschild radii in diameter, larger than the event horizon itself due to gravitational lensing effects. For Sagittarius A star, this meant an angular size of about 50 micro-arcseconds. The paper argued that this was just barely within the reach of very long baseline interferometry observations at wavelengths of 1 millimeter or shorter. Crucially, Falcke and his colleagues predicted that observing this shadow was not just theoretically possible, but practically achievable with existing technology, properly combined. They weren't proposing a telescope that needed to be invented. They were proposing a new way to use telescopes that already existed. Falcke had invented a term that would become famous, the black hole shadow. He had also sketched out how to see it. The shadow of a black hole is not the same as its event horizon. This distinction is crucial for understanding what the Event Horizon Telescope actually imaged. The event horizon is the actual boundary of the black hole, the point of no return, defined by the Schwarzschild radius for a non-spinning black hole, or the more complex Kerr metric for a spinning one. Cross the event horizon and you're gone, falling inexorably toward the singularity at the center. But the shadow is larger, typically about 2.5 times the diameter of the event horizon. Why? Because of the photon sphere. At a distance of about 1.5 times the Schwarzschild radius, light can orbit a black hole. Not escape, orbit. Photons at this distance are balanced on a knife's edge. Falling in would mean capture, while moving slightly outward would allow escape. This spherical shell of unstable photon orbits is called the photon sphere. No physical object can orbit at the photon sphere. Such orbits are unstable, and any perturbation would send the orbiting object spiraling in or flying away. But photons, massless and moving at the speed of light, can briefly maintain these precarious orbits before their inevitable fate. Light passing near this region gets dramatically deflected. A photon that passes just outside the photon sphere might complete one or more loops around the black hole before finally escaping. Some photons orbit multiple times, creating layers of increasingly thin rings in the observed image. The mathematics predicts an infinite sequence of such rings, each progressively fainter and thinner than the last. The result of all this gravitational lensing is that the apparent size of the dark region, the shadow, is magnified. Light from behind the black hole is bent around it, piling up at the edge of the shadow and creating a bright ring. Light that passes closer is captured. The boundary between these two fates creates a sharp edge, the photon ring. The shadow of the black hole in M87, the first one ever imaged, has a diameter of about 40 billion kilometers, larger than the orbit of Pluto around the Sun, larger than the entire solar system out to the Kuiper belt. The actual event horizon is smaller, measuring just under 40 billion kilometers across, roughly 2.5 times smaller than the shadow it casts. So when we look at that famous orange ring image, we're seeing light that passed close to the black hole, but managed to escape. Some of that light orbited the black hole multiple times before breaking free. The dark center is where light fell in and never came back. We're not seeing the black hole. We're seeing what the black hole does to light around it, a cosmic silhouette against the background of its own destruction. Understanding what you need to see is one thing. Building a telescope capable of seeing it is another. The supermassive black hole at the center of M87, despite being 6.5 billion times more massive than our Sun, lies 55 million light-years away. At that distance, even its enlarged shadow appears incredibly small in the sky. To appreciate what 6.5 billion solar masses means, consider this. Our Sun contains enough mass to make 330,000 Earths. M87 star contains enough mass to make 6.5 billion suns. That's more than 2 trillion Earths worth of matter, compressed into a region smaller than our solar system. M87 itself is a monster galaxy, a supergiant elliptical located at the heart of the Virgo cluster, a collection of about 2,000 galaxies, roughly 55 million light-years from Earth. The galaxy contains several trillion stars, perhaps 10 times as many as the Milky Way, and its supermassive black hole is one of the largest ever measured. This black hole was first detected indirectly in 1978 when astronomers studying the motions of stars near M87's center found they were orbiting something extremely massive and compact. The stars were moving too fast to be gravitationally bound by visible matter alone. Something dark and heavy sat at the galaxy's heart. In 1994, the Hubble Space Telescope measured a disk of hot gas spiraling toward M87's center at speeds of over 1 million miles per hour. From these velocities, astronomers calculated that the central object contained billions of solar masses compressed into a space smaller than our solar system. There was no known object that could fit that description except a black hole. M87 also produces one of the most spectacular jets in the universe. A beam of matter and radiation shooting out from near the black hole at nearly the speed of light, extending for thousands of light-years into intergalactic space. This jet, first photographed in 1918, was one of the first hints that something extraordinary was happening in M87's core. How small? About 40 micro-arcseconds. To put that in perspective, there are 3,600 arcseconds in 1 degree. The full moon spans about half a degree, or 1,800 arcseconds. 40 micro-arcseconds is 40 millionths of an arcsecond. Another way to think about it, if you held up a grain of rice at arm's length, it would span about 60 arcseconds, 150,000 times larger than M87 star's shadow. The black hole shadow is so small that to see it, you would need vision 150,000 times sharper than the ability to see a grain of rice at arm's length. Shepard Doeleman, who would become the director of the Event Horizon Telescope project, offered several vivid analogies. It's like trying to photograph an orange on the surface of the moon from Earth, or reading a newspaper in New York while sitting at a cafe in Paris, or counting the dimples on a golf ball in Los Angeles from New York. Each of these comparisons drives home the same point. The angular resolution required is absurdly, impossibly fine. No single telescope on Earth can achieve this resolution. The sharpness of a telescope image is limited by the diameter of its mirror or dish. Larger telescopes can distinguish finer details. This is expressed by the Rayleigh criterion. The minimum angle two objects can be separated by and still be distinguished is approximately the wavelength of light divided by the diameter of the telescope. To resolve something 40 microarc seconds across at a wavelength of 1.3 millimeters, you would need a telescope with a diameter of about 10,000 kilometers. That's roughly the diameter of the Earth. Obviously, building a solid telescope dish the size of a planet is impossible. The engineering challenges would be insurmountable. Such a structure couldn't support its own weight. It couldn't be pointed. It couldn't exist. But there's another way. In the 1950s and 60s, radio astronomers developed a technique called Very Long Baseline Interferometry, or VLBI. The concept is elegant. If you observe the same radio source with multiple telescopes scattered across great distances, you can combine their signals to achieve the resolution of a single telescope with a diameter equal to the separation between them. The physics behind this is the wave nature of light. When radio waves from a distant source reach two widely separated telescopes, they arrive at slightly different times depending on the angle of the source in the sky and the distance between the telescopes. By measuring these tiny time differences, measured in billionths of a second, astronomers can extract detailed information about the source's structure. It's not simple. The signals from each telescope must be recorded with exquisite timing precision using atomic clocks called hydrogen masers that keep time accurate to within trillionths of a second. Each telescope must track the source perfectly, compensating for Earth's rotation, atmospheric disturbances, and the tiny variations in our planet's spin. The data must then be transported to a central location and correlated, matching up the radio waves captured at each site. The correlation process is painstaking. The computers must try billions of possible alignments of the data, searching for the combination that produces coherent signal rather than noise. Even tiny errors in timing or position can destroy the correlation entirely. When it works, the result is astonishing. A network of radio telescopes spanning continents can achieve the resolution of a telescope the size of those continents. The Event Horizon Telescope pushed this concept to its limit. Beginning in the early 2000s, a global collaboration began assembling a network of radio observatories specifically designed to image black hole shadows. The telescopes included the Atacama Large Millimeter Array in Chile, a collection of 66 dishes that can be combined into a single highly sensitive instrument, the Sub-Millimeter Array in Hawaii, the Large Millimeter Telescope in Mexico, the South Pole Telescope in Antarctica, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell Telescope in Hawaii, and several others spread across 4 continents. Each telescope had to be equipped with specialized electronics designed by the Event Horizon Telescope collaboration, high-speed digital recorders capable of capturing 64 gigabits per second, hydrogen maser atomic clocks, and custom signal processors. The technical requirements were extreme. The observations had to be synchronized across the globe to within fractions of a picosecond, a trillionth of a second. When observing together, these telescopes formed a virtual instrument the size of Earth itself, finally achieving the resolution needed to see a black hole's shadow. But resolution is only part of the challenge. The telescopes also had to observe at just the right wavelength. The Event Horizon Telescope operates at a wavelength of 1.3 millimeters, in the sub-millimeter range of the radio spectrum. This choice was deliberate and carefully considered. At longer wavelengths, the resolution wouldn't be fine enough, even with Earth-sized baselines. At shorter wavelengths, Earth's atmosphere absorbs too much of the radiation. Water vapor in the air blocks sub-millimeter waves, which is why the Event Horizon telescopes are located at high, dry sites where the atmosphere is thinnest. And crucially, at 1.3 millimeters, the radiation can pierce through the gas and plasma surrounding black holes that would block visible light. The material around a black hole scatters light, creating a kind of cosmic fog. But this scattering decreases at shorter wavelengths. At 1.3 millimeters, the universe becomes just transparent enough to see through to the event horizon scale. It was like finding a cosmic window, a specific frequency at which the universe became briefly transparent, revealing what had always been hidden. In April 2017, 8 radio observatories across 6 geographic locations turned simultaneously toward 2 targets: Sagittarius A star, the 4 million solar mass black hole at the center of our Milky Way, and M87 star, the supermassive giant 6.5 billion times the mass of our Sun, sitting at the heart of a galaxy 55 million light-years away. The timing had to be perfect. Weather conditions at all sites had to be favorable. Any clouds or humidity could absorb the sub-millimeter radiation. The observations required clear skies at locations as distant as Antarctica and Hawaii simultaneously. For 4 nights, when conditions aligned, the telescopes collected data. Each night, each telescope recorded approximately 350 terabytes of information onto banks of helium-filled hard drives. So much data that it couldn't be transmitted over the internet. The total data volume approached 5 petabytes, equivalent to 5,000 years of MP3 audio, or the complete selfie collection of 40,000 people over their entire lifetimes. The hard drives were physically shipped to correlation centers at MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy in Germany. Doleman would later joke that nothing beats the bandwidth of a plane full of hard drives. The data from the South Pole telescope was particularly problematic. The Antarctic winter had already begun, making flights impossible. The hard drives from the South Pole didn't arrive until December 2017, 8 months after the observations. Until that data arrived, the collaboration couldn't complete the correlation. The South Pole's position was crucial for filling in gaps in the virtual telescope's coverage of the sky. Then began the arduous process of correlation and imaging. The signals from each telescope had to be synchronized to within fractions of a trillionth of a second. The correlation computers at MIT and Germany worked through billions of possible alignments of the data, searching for the combinations that produced coherent signal. The imaging process was even more challenging. Unlike an optical telescope that directly produces an image, an interferometer measures what are called visibilities, essentially the strengths of different spatial frequency components of the image. Converting these visibilities into an actual picture requires sophisticated algorithms and careful assumptions about the source structure. To avoid bias, the collaboration divided into 4 independent teams. Each team used different imaging algorithms and worked in complete isolation, not sharing their results until all teams had finished. If the teams produced similar images using different methods. That would be strong evidence that the images were real, not artifacts of the processing. Multiple independent teams used different algorithms to reconstruct images from the data, working in isolation to avoid influencing each other's results. What emerged was consistent across all teams, a bright ring of emission surrounding a dark central shadow. The ring was slightly asymmetric, brighter on one side, exactly as predicted by general relativity for a spinning black hole, whose accretion disk is partially approaching and partially receding from Earth. "We have seen what we thought was unseeable," Delleman announced on April 10th, 2019. "We have seen and taken a picture of a black hole." Let's be precise about what that picture actually shows. We are not seeing the black hole. We cannot see the black hole. The black hole is the darkness in the center, the absence of light, the region from which no information can escape. What surrounds that darkness is light from the accretion disk and from photons that came close to the event horizon but managed to escape, their paths dramatically bent by gravity. The orange color is not real. Radio waves have no color. The human eye cannot see them. The Event Horizon Telescope observes at a wavelength of 1.3 millimeters, invisible to us. The color was added during image processing to make the intensity of the radiation visible, with brighter regions shown in warmer tones. The collaboration chose a golden orange palette that conveys the heat and energy of the environment, though they could have chosen any color scheme. The asymmetric brightness is real and deeply meaningful. One side of the ring is brighter because the accretion disk is spinning at nearly the speed of light. Material on the side moving toward Earth has its light boosted by the relativistic Doppler effect, a consequence of special relativity that makes approaching objects appear brighter and bluer, while receding objects appear dimmer and redder. For material moving at significant fractions of light speed, this effect is dramatic. In M87 star, the southern portion of the ring is brighter than the northern portion, indicating that the material is moving toward us on that side. From this asymmetry, scientists could determine that the accretion disk is oriented with its spin axis pointing roughly away from Earth, tilted at about 17 degrees from our line of sight. The ring itself is not the accretion disk seen edge-on, though it's easy to mistake it for that. The physics is more complex. We're seeing a combination of direct emission from the disk, light that has been bent around the black hole by gravitational lensing, and light that has completed one or more partial orbits before escaping. These different contributions layer on top of each other, creating the bright ring we observe. The mathematics of general relativity predicted this ring structure decades before it was observed. The prediction isn't just that we'd see a ring. It's that the ring would have a specific size relative to the black hole's mass, a specific thickness, and a specific brightness profile. All of these match what was observed, and the shadow in the center, measuring about 40 micro arcseconds across, is consistent with a black hole of 6.5 billion solar masses, exactly as predicted from decades of studying stellar and gas dynamics in M87. Einstein's theory, formulated 104 years earlier, had passed perhaps its most dramatic test. The shadow of M87 star confirmed several key predictions of general relativity. The shape was nearly circular, deviating from perfect roundness by less than 10%. exactly as predicted for a Kerr black hole. A black hole with spin. The size matched what Einstein's equations said it should be for a black hole of that mass. The polarization patterns detected in later observations revealed ordered magnetic fields threading through the accretion disk, consistent with theoretical models of how matter falls into supermassive black holes. Every observation matched. Every prediction was verified. There is a beautiful historical symmetry here. In 1919, exactly 100 years before the M87 star image was released, two scientific expeditions set out to test Einstein's new theory of general relativity. One traveled to the island of Principe off the coast of Africa. The other went to Sobral in Brazil. Their goal was to observe a total solar eclipse and measure whether starlight passing near the sun was bent by its gravity, as Einstein predicted. The experiments were difficult, weather threatened to ruin the observations. The photographic plates were hard to analyze, but when British astronomer Arthur Eddington announced the results, they confirmed Einstein's prediction. Light was bent by the sun's gravity exactly as general relativity said it would be. That confirmation made Einstein a celebrity and transformed physics. A century later, the Event Horizon Telescope team echoed those eclipse expeditions, not measuring the bending of starlight by the sun, but observing the extreme warping of space-time around a black hole 6.5 billion times more massive. The connection was deliberate. The Event Horizon Telescope observation campaign of April 2017 was timed, in part, to coincide with the centennial of the 1919 eclipse observations. The scientists involved saw themselves as continuing a tradition, testing Einstein's most extreme predictions in environments that would have seemed like science fiction to Eddington and his colleagues. This matters because general relativity is a theory that has survived every test we've thrown at it for over a century, from the precession of Mercury's orbit to the detection of gravitational waves in 2015. But those tests probed relatively weak gravitational fields. The environment around a black hole's event horizon is where gravity reaches its most extreme, where space-time is most dramatically curved, where the consequences of Einstein's equations become most bizarre. If general relativity were going to break down anywhere, it would be here. It didn't. The image of M87 star showed that Einstein's equations, worked out with pen and paper in 1915 by a man who couldn't have imagined radio telescopes or digital computers or global scientific collaborations, correctly describe the behavior of space-time even in the most extreme gravitational environment we can observe. 3 years later, in May 2022, the Event Horizon Telescope collaboration released a second image, the shadow of Sagittarius A star, the black hole at the center of our own galaxy. This image was, in many ways, more challenging than M87 star. Though Sagittarius A star is much closer, about 27,000 light-years away compared to 55 million, it's also about 1,500 times less massive. This smaller mass means everything happens faster. Gas orbits M87 star in days to weeks. Gas orbits Sagittarius A star in mere minutes. To understand the difference, consider this. M87 star has a mass of 6.5 billion suns compressed into a region about as large as our solar system. Its event horizon has a diameter of about 24 billion miles, roughly the size of Neptune's orbit around the Sun. Light takes several days to complete one orbit around this monster. Sagittarius A star, with only 4 million solar masses, has an event horizon about 14 million miles across, roughly the size of Mercury's orbit. Light orbits this black hole in about 25 minutes. Gas in the accretion disk moves even faster relative to the timescales of observation. During the observing window, Sagittarius A star was changing. It was, as one scientist put it, like trying to photograph a puppy chasing its tail. Every few minutes, the brightness distribution around the black hole would shift as hot gas orbited and flared. The team had to develop sophisticated new computational techniques to account for this variability, essentially averaging together many possible snapshots of a rapidly changing source. There was another challenge unique to Sagittarius A star. Between us and the galactic center lies 27,000 light-years of interstellar gas and dust. This material scatters radio waves, blurring the image. The effect is similar to how looking at a streetlight through a foggy windshield creates a smeared halo instead of a sharp point. The Event Horizon Telescope team had to model and correct for this interstellar scattering to extract the true structure of the source. Despite these obstacles, the result was unmistakable. Another ring of light surrounding a dark center, our galaxy's heart, finally revealed, or rather finally inferred from the light it couldn't quite capture. The two images now stand as bookends. M87 star, one of the most massive black holes known, and Sagittarius A star, the modest giant at the center of our own spiral home. Together, they demonstrate that black holes, these predictions of Einstein's equations, these objects that were once considered impossible, are real, are common, and behave exactly as the theory predicted they would. But there's something deeper here than a test of a theory. When you look at that image, that blurry orange ring surrounding darkness, you are looking at the edge of the knowable universe. Not in the sense of distance, but in the sense of information. Beyond that dark center lies a region from which no information can ever reach us. What happens inside the event horizon is forever sealed from the outside universe. This is not a limitation of our technology. It's not something we might overcome with better telescopes or more clever techniques. It is fundamental. The universe has a built-in boundary between what can and cannot be known. Consider what this means. Inside that dark region, matter and energy continue to exist. Stars have fallen in there. Perhaps planets, perhaps entire civilizations, if such things ever came too close. The black hole grows more massive with every particle it captures, but we will never know what happens to any of it. The event horizon is an absolute epistemic barrier, a wall beyond which knowledge cannot pass. Some physicists find this troubling. The event horizon creates what's known as the information paradox. Quantum mechanics says information cannot be destroyed. It's a fundamental principle, without which the entire framework of quantum physics collapses into inconsistency. Yet black holes seem to erase information permanently. When a book falls into a black hole, all the information encoded in its pages, every word, every arrangement of atoms, disappears from the accessible universe. This apparent contradiction has sparked decades of theoretical work. Stephen Hawking's famous discovery that black holes emit radiation, now called Hawking radiation added another layer to the puzzle. Hawking showed the black holes aren't entirely black. Quantum effects near the event horizon cause them to slowly radiate energy and shrink over unimaginably long timescales. Eventually, a black hole will evaporate entirely, but here's the problem. Hawking radiation appears to be completely thermal, carrying no information about what fell into the black hole. If a black hole can completely evaporate and its radiation carries no information, then information has been destroyed, violating quantum mechanics. The information paradox remains unsolved. Proposed solutions range from the suggestion that information is somehow encoded in the Hawking radiation in ways we don't yet understand, to the radical idea that the interior of a black hole might be replaced by a firewall of high-energy radiation that incinerates anything that crosses the horizon. Some physicists have even suggested that information might escape through wormholes to other regions of space-time. The Event Horizon Telescope can't directly address the information paradox. That would require probing the event horizon itself, which is precisely what the laws of physics forbid. But by providing precise measurements of black hole shadows, the Event Horizon Telescope can test the limits of general relativity and potentially reveal hints of new physics. Others find the existence of event horizons strangely comforting. In a universe that often seems fully mapped and explained, here is genuine mystery. Here is a place where our physics reaches its limit, where the known transitions into the fundamentally unknowable. When Dürlemann described a black hole as a one-way door from our universe, he captured something essential. The event horizon is not just a physical boundary, it's an epistemological one. It marks the edge of what we can ever hope to learn through observation. The Event Horizon Telescope continues its work. Additional telescopes have joined the network, including the Greenland Telescope and the Northern Extended Millimeter Array in France. Observations at shorter wavelengths promise even finer resolution. The collaboration recently achieved the highest resolution ever from Earth's surface by observing at 0.87 millimeters, a 50% improvement over the original observations. At this shorter wavelength, the Event Horizon Telescope could theoretically see details as fine as 13 micro-arcseconds, like observing a bottle cap on the Moon from Earth. This improved resolution would allow scientists to probe even closer to the event horizon, potentially revealing new details about how matter behaves in the most extreme gravitational environments in the universe. Future observations may reveal the photon ring, a thin, sharp feature created by light that has orbited the black hole multiple times before escaping. Current images show a broad ring of emission, but theory predicts that embedded within this broad ring should be a series of increasingly thin subrings, each created by light that completed more orbits before reaching us. Detecting these subrings would provide an exquisitely precise test of general relativity, potentially allowing detection of deviations from Einstein's predictions if they exist. There's also talk of expanding the Event Horizon Telescope beyond Earth. A telescope in space, orbiting far from our planet, could extend the baselines far beyond the diameter of Earth, potentially allowing observations of smaller black holes or revealing finer structure around the ones we've already imaged. Concepts for such space-based extensions are already being studied. The collaboration is also working on creating movies of black holes. By observing the same target repeatedly over months or years, scientists hope to watch the evolution of the accretion flow in real time, or at least as close to real time as observing objects millions of light years away allows. For M87 star, where changes unfold over days to weeks, this is feasible with current technology. The collaboration has already released images showing how M87 star's accretion disk changed between 2017 and 2018. And there are more black holes to photograph. The collaboration has observed several other supermassive black holes and blazars, including the distant quasar 3C279, capturing images that reveal the base of its relativistic jet, matter being accelerated to nearly the speed of light and hurled across intergalactic space. One particularly ambitious project is the Africa Millimeter Telescope, planned for Namibia's Gamsberg Mountain. This new telescope would fill a crucial gap in the Event Horizon Telescope's global coverage, enabling observations during more of the Earth's rotation and significantly improving image quality. It would also be the first millimeter wave telescope on the African continent, opening new possibilities for astronomical research. Each addition to the network improves not just resolution, but image fidelity, the ability to accurately reconstruct complex structure from the sparse data that interferometry provides. The more telescopes, the more complete the picture. When Heino Falcke first proposed that we could image a black hole shadow, many of his colleagues were skeptical. The technical challenges seemed insurmountable. The distances were too vast, the details too fine, the required precision too extreme. Some doubted it would ever be possible. The atmosphere would distort the signals too much. The telescopes couldn't be synchronized precisely enough. The imaging algorithms wouldn't be able to handle the sparse, noisy data. But Falcke understood something important. The impossibility of photographing a black hole directly is precisely what makes it possible to photograph a black hole at all. Think about that for a moment. If black holes emitted light like stars do, we would be overwhelmed by radiation. We wouldn't see a shadow. We'd see a blinding point of light, impossible to resolve into structure, its internal features washed out by its own brilliance. It's the darkness of black holes that creates the contrast. It's their fundamental opacity that casts the shadow. The Event Horizon Telescope didn't overcome the laws of physics. It worked with them. It exploited the very property that makes black holes black, their absolute refusal to emit light, to create an image of precisely that refusal. We cannot see a black hole. We see its absence, and that absence tells us everything. The shadow is not a limitation. It's the message. In 2020, the Event Horizon Telescope collaboration was awarded the Breakthrough Prize in Fundamental Physics, recognizing the work of more than 347 scientists from 60 institutions across 20 countries. The prize citation noted that the team had achieved something presumed to be impossible just a generation ago. The prize money, $3 million, was split among all 347 researchers, from senior professors to graduate students. It was a recognition that modern science is fundamentally collaborative, that breakthroughs come not from lone geniuses, but from coordinated teams working across continents and time zones. Consider what the project required. Telescopes in Chile had to coordinate with telescopes in Antarctica, which had to coordinate with telescopes in Spain and Mexico and Hawaii. Each site had its own weather concerns, its own technical challenges, its own time zones. The observations had to happen simultaneously, with split-second precision, across a planet spinning on its axis. The data couldn't be transmitted over the internet. The files were too large and the networks too slow. Instead, 1/2 ton of hard drives had to be physically transported to correlation centers. The South Pole data was literally frozen out of reach for 8 months, waiting for Antarctic summer to allow flights. When the data finally came together, the analysis required supercomputers running for months. The imaging algorithms were developed by teams in Massachusetts and Germany and the Netherlands. Quality control checks were performed by groups in Japan and Taiwan. The final results were reviewed by hundreds of scientists before publication. This is what big science looks like in the 21st century. It's not a single flash of insight, but years of painstaking preparation. It's not one person with a telescope, but thousands of people with specialized skills, each contributing a piece to a puzzle that none could solve alone. I think many people marveled at what humanity could do by working together, Doleman said after the announcement, in an age when so many issues tend to divide us. But perhaps the most remarkable aspect of the achievement is not the technology or the science, extraordinary as both are. It's what the image represents about human curiosity and persistence. For over a century, physicists had theorized about black holes. They had calculated their properties, debated their existence, wondered about their nature. They had accepted that these objects, by definition, could never be directly observed. Black holes were mathematical constructs, predicted by equations, inferred from indirect evidence. And then, through decades of patient work, through the development of new technologies and techniques, through global collaboration and meticulous observation, we found a way to see them anyway. Not see them directly, that remains impossible and always will be, but to see their shadows, to capture the darkness they create against the light they bend but cannot hold. Karl Schwarzschild died in 1916 without knowing that his solution to Einstein's equations described objects that would one day be found throughout the universe. He thought his mathematics were a curiosity, an interesting feature of the equations with no physical reality. The letter he received from Einstein, expressing astonishment that an exact solution could be formulated so simply, gave no hint of what his work would ultimately mean. Neither man could have imagined that a century later, telescopes spanning the Earth would combine to photograph the very phenomenon Schwarzschild had mathematically described. 103 years after Schwarzschild sent his solution to Einstein, the Event Horizon Telescope captured an image of exactly what his equations predicted. A dark region about 2.5 times the Schwarzschild radius, surrounded by light bent according to the geometry he first described. John Wheeler, who gave black holes their name, died in 2008, 11 years before the first image was released. He spent decades championing the study of black holes when most physicists considered them theoretical oddities. He supervised doctoral students who would become leaders in the field. Kip Thorne, who won the Nobel Prize for detecting gravitational waves. Jacob Bekenstein, who discovered that black holes have entropy, and many others who carried forward his vision. Wheeler was famous for his aphorisms. The black hole teaches us that space can be crumpled like a piece of paper into an infinitesimal dot, he wrote, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but. He died believing in black holes, convinced by theory and indirect evidence. But he never saw one. Heino Falcke, who coined the term black hole shadow and predicted it could be observed using millimeter wavelength VLBI, was there in Brussels on April 10th, 2019, watching as the image he had dreamed of for decades appeared on screens around the world. "It has been an emotional journey," he said afterward. "It started from when I was a PhD student." In his 2000 paper with Melia and Argol, Falcke had not only predicted the existence of the shadow, but had calculated its approximate size and shape. He had argued that a network of radio telescopes could achieve the resolution needed to see it, and he had been instrumental in building that network, serving as chair of the Event Horizon Telescope Science Council. The journey from prediction to observation had taken nearly 20 years. Falcke later described it as the most emotionally overwhelming experience of his scientific career. "We set out to see the unseeable," Doeleman said. "We needed to build a telescope as large as the Earth to do it, and we pulled it off. There's a photograph on my wall of the Earth taken from 4 billion miles away by the Voyager 1 spacecraft in 1990. In it, our planet appears as a pale blue dot, barely a pixel, suspended in a beam of scattered sunlight. The photograph was taken at Carl Sagan's request, as Voyager was leaving the solar system and turned its camera back for one last look at home. Sagan, who died in 1996, wrote about it beautifully. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives," he went on. "The Earth is a very small stage in a vast cosmic arena. Our planet is a lonely speck in the great enveloping cosmic dark. The image of M87 star is, in a sense, the inverse of that photograph. It shows not where we are, but where nothing can be. It shows not a tiny speck of light containing all we know, but an absence of light so complete that it defines the edge of the observable universe. The pale blue dot humbles us with distance, with how small we are compared to the vastness of space. The black hole shadow humbles us with impossibility, with the existence of places in the universe from which nothing, not even light, can ever escape. And yet both images evoke the same humility. We are small. The universe is vast. There are places we will never go, things we will never fully understand, boundaries we will never cross. But we can look, we can calculate, we can build instruments of extraordinary precision and point them at the sky. We can take the equations Einstein wrote in his study in Bern, scribbling on paper with pen and ink, and verify them against the light from a galaxy 55 million light-years away. Light that began its journey toward Earth when our ancestors were just developing stone tools. We cannot photograph a black hole directly, but we can photograph its shadow. We can capture the edge of darkness. We can see, in the truest sense, what cannot be seen. And somehow, against all odds and all logic, that is enough. On that April day in 2019, Doeleman described the moment he first saw the signals that would become the image of M87 star. Years earlier, while working at MIT's Haystack Observatory, he had detected the first faint hints of structure near Sagittarius A star, the first evidence that something of event horizon scale could be resolved. He had been running observations at the Arizona Radio Observatory's submillimeter telescope in 2007 when the first detections came through. The signals showed that Sagittarius A star had structure on scales of just a few Schwarzschild radii, meaning the emission was coming from right at the edge of the black hole. I started seeing these very faint detections, Dolleman recalled. So I ran some analyses to tighten up the data, and suddenly, these detections came out. That was a moment, he said, where there was one person on the planet who knew what had just happened. That was a moment, he said, where there was one person, me, in the world who knew what had just happened. That was pretty amazing. It was also the moment that launched the modern Event Horizon Telescope, because as soon as they knew there was structure there, as soon as they confirmed that the emission region was small enough to image, the race was on. As soon as we knew there was something there, Dolleman said, the gloves came off and we were ready to start building an Earth-sized array to image it. 12 years later, that array delivered. Science is often portrayed as a gradual, methodical process, and it is, but it's also punctuated by moments of revelation, moments when years of work suddenly crystallize into knowledge that no one possessed before. The image of a black hole's shadow was one such moment. For the first time in human history, we could point to a picture and say, there is the boundary between everything we can know and everything we never will. There is the edge of physics. There is the unseeable, finally seen. A black hole, if you looked at it naked, would be invisible. That's what Dolleman said during one of the press conferences. It's nature's most amazing invisibility cloak. But we found a way around it. Not by making the invisible visible. That's impossible, forbidden by the very laws of physics that govern the universe. But by looking at what the invisible does to the visible, by capturing the shadow it casts, the light it bends, the absence it creates. In the end, that's what all of science does. We cannot directly observe quarks. We see only the tracks they leave in particle detectors. We cannot directly observe dark matter. We see only the gravitational effects it has on galaxies. We cannot directly observe the early universe. We see only the afterglow of the Big Bang, light that has traveled for nearly 14 billion years to reach us. A black hole is simply the most dramatic example. The ultimate invisibility, the perfect darkness, an object that by definition cannot reveal itself to us directly. And yet, there it is, a blurry orange ring surrounding nothing. Evidence of the most extreme gravity in the cosmos. Confirmation of equations written by a German physicist who reimagined the universe while serving as a patent clerk in Bern. The first direct visual evidence that these strangest of objects, predicted by theory, inferred from indirect observations but never seen, actually exist. We have taken a picture of a black hole, or rather, we have taken a picture of everything a black hole is not. We have photographed the light that escaped. The darkness in the center is where the story ends, where matter and energy fall beyond the reach of any observation, any instrument, any future technology. That darkness is the black hole, and in seeing the darkness, in capturing the absence, the void, the silence, we have learned something profound about the limits of what can ever be known. We have seen what we thought was unseeable. And the darkness in the center of that image, the shadow of something from which light cannot escape, tells us more about the universe than any brightness ever could. Because the darkness is real. The darkness is the point. And in seeing it, we have pushed human knowledge to its absolute boundary, the edge of the event horizon, where physics ends and the unknowable begins. That is what the Event Horizon Telescope captured. Not a black hole, something better. The silhouette of mystery itself. The proof that even in a universe where so much remains unknown, human beings can push back the darkness, not by dispelling it, but by seeing its shape, measuring its edges, and understanding what it means. The darkness cannot be illuminated, but it can be observed. And in observation, there is a kind of victory over the unknowable. We have seen the unseeable. The shadow endures.